So in this video what we're going to do is to look at the quotient rule of differentiation, which is a rule that we can use to differentiate a ratio or quotient of two functions. And I've written the rule out here. And what I want to point out in this video is that the quotient rule is actually equivalent to use of the product and the chain rule on such a ratio. And then I'm going to talk about where it might be somewhat inefficient to use the quotient rule in this way, and we're more efficient if we just think of it as the product and the chain rule. So what I'm going to do now is just pause and make a bit of room. So to see how we can differentiate this, what I want to do now is I want to look at the quotient that we have and write it in an equivalent way. So note that such a quotient, f of x over g of x, can be written as f of x multiplied by, and then it's 1 over g of x is the other factor, and I'm going to use several sets of brackets. So I've got g of x all to the minus 1, and I have another set of brackets here. So I have a factor multiplied by another factor, and the second factor involves the reciprocal 1 over g of x. And I would like to emphasize that I really do need to use brackets here or some other equivalent notation, because if I write g to the minus 1 of x, if I was to put the power here, I would mean the inverse function and not the reciprocal function, and this equality would be wrong. So, written in this way, we realize that much more easily how we can use the product rule to differentiate this. We have something multiplied by something, so we can use the product rule. So let me just pause and make a bit of room. So, the product rule, let's just recall what it tells us. So, recall the product rule. And what this tells us is that the derivative of a product of two functions, let me call them u and v, just so as to not use the same symbols, is given by the derivative of u, I'm just using dash notation for brevity here, multiplied by v of x, plus the first factor, u, multiplied by the derivative of the second factor, in this case v. So that's the product rule that we're going to need, so I'll just pause, make some room. And the other law of differentiation, or rule of differentiation, that we're going to need is the chain rule. So let's also recall how the chain rule works in the case that we have a function raised to a power. This is sometimes called the chain rule for powers. So let's also recall the chain rule for powers. And this tells us that if we're differentiating a function, and in this case I'm going to say that the function is g of x raised to some power n, and the reason I'm calling it g is because here we have g, is given by, well, we take the power n and we bring it down in front, so we write n down, we then multiply it by g of x to the power n minus 1, and then we multiply this by the derivative of the function g, so g dash of x. So this is the chain rule for powers that we're also going to need. So let me just pause and make a bit of room. So here I've written the two rules that we're going to need, the product rule and the chain rule for powers, and now we're going to differentiate this quotient, but written in this way. So therefore what we're going to get is that the derivative with respect to x of f of x over g of x is given by, so looking at it here we have a product, the first term is f, so we have the derivative of f dash of x, multiplied by the second term in the product, and the second term in the product is 1 over g of x, so I can just write this as 1 over g of x. I could write it here, but it's shorter just to immediately write over g of x here. The second term that we get involves our first factor here, just being written out, so I can write I'll skip the plus sign for a moment, f of x, multiplied by the, well no, I will put the plus sign in, the derivative of g of x all to the minus 1. So the reciprocal of g of x. And now to differentiate this factor, we're going to need the chain rule for powers. So let me just pause and make a bit of room. So therefore, our result is going to be equal, the first term is unchanged, it's the derivative of f divided by g. In the second term, we have f of x, and now when we differentiate this factor here, we're differentiating a function raised to the power of minus 1. So from the chain rule for powers, we bring the power down in front, so we bring down a factor of minus 1, and that will change the plus sign in front into a minus sign. We then have g of x raised to the power of, and now it's going to be minus 1 with 1 subtracted from it, so we get minus 1 is minus 2, multiplied by the derivative of the function g of x that was in the brackets. So this is multiplied by the derivative of our function g of x. So we see here that we have the function f of x multiplied by the derivative of g of x. That's exactly what we have here, and it's multiplied by g of x to the power minus 2, so it is 1 over g of x squared. So that's that factor here on the bottom. So let me pause and make some room. So what we see that we get now is the first term here is unchanged, so we have the derivative of f divided by g, and then we subtract from it f of x times the derivative of g of x, and then this is divided by 2 powers of g of x, so we have on the bottom g squared of x. And if we wish, we can put these on a common denominator, and the common denominator is g of x squared. And in the numerator here, if we want to put this over g squared of x, we must multiply the numerator here by g of x. So that's exactly what we're going to do. We write the derivative of f of x multiplied by g of x minus f of x multiplied by the derivative of g of x. And if we compare this result with here, we see that we have simply rederived the chain rule, the quotient rule rather. We've rederived the quotient rule from the product rule and the chain rule for powers. So what I want to do now is to go on to another slide and to look at an example where using the quotient rule written in this way is less efficient than doing it in this way here, in other words using the product and the chain rule for powers. So I've written here for reference the quotient rule, and I want to use it now to differentiate the sine of x divided by x to the fourth. So our numerator is the sine of x, so I'm going to differentiate that, and I get the cosine of x multiplied by the denominator, which in this case is x to the fourth, minus, and then we take the sine of x, that was our original numerator, and we multiply that by the derivative of the denominator, and the denominator was x to the fourth, so we pull a 4 down and subtract the 1 from the power, so it's 4x cubed, and then we divide by the denominator squared, so it's x to the 4th squared, and x to the 4th squared is x to the 8th. So that is a result for it, and we now realise that there is a common factor of x cubed here and in the x to the 4th, so we could pull outside of the whole of the numerator a factor of x cubed, and we can cancel that with 3 of the powers of x on the bottom, leaving us with a power of x to the 5th. So if I want to do that very slowly indeed, what I would have would be x cubed times the cosine of x times an x minus, I'll put the 4 in front, times the sine of x, all divided by, and I'm going to split the x cubed off from the x to the 8th, so it's x cubed times x to the 5th. And then, as we've said, these factors here will cancel. So therefore, what we get overall is, now the first term I'm going to write the x in front, so I have x times the cosine of x minus 4 times the sine of x, and all divided by x to the 5th. So that's an example of how to use the quotient rule, but what I'd like to do now is I'd like to calculate exactly the same derivative, differentiate the same function, but using the chain rule and the product rule. So I'll go on to a new slide to do that. So the alternative method for differentiating this function here, sine of x divided by x to the 4th, is to think of this as a product, the sine of x multiplied by x to the minus 4, and then we just use the product rule and the chain rule for powers. So from differentiating the sine of x, we get the cosine of x multiplied by x to the minus 4, which I can immediately put as 1 over x to the 4 on the bottom. And then we're going to have the sine of x multiplied by the derivative of x to the minus 4. We pull, therefore, a factor of minus 4 down, I'll put them in front, times x to the minus 5, I subtract 1. I could, of course, have just written this as over x to the 5th. So if I want to do that, and I want to put these things on a common denominator of x to the 5th, what I will get is on the top I need to put an x in front of the cosine of x, so that that is exactly the same as this factor here if I was to cancel the x with one of these powers. And then I have to subtract minus 4 times the sine of x. So we see that both methods, using the quotient rule or using the product rule together with the chain rule for powers, are equivalent. And I would say that generally speaking, if you have the denominator to a higher power, this is a more efficient route than the previous slide. You may want to think about whether you agree or disagree with me. And also I would say that if we're using it this way, it's just, we don't need to really think about the quotient rule. It is just the product rule and the chain rule for powers, and that's all we really have. Okay, so I'll stop this video here.